Hello, my name is Konrad Sztyber. I work at Intel, and I'm one of the SPDK core maintainers. Today, together with my colleague, Karol Latecki, I will be talking about how we achieve such ludicrous performance like the 18 millions mentioned in the title using SPDK, and how you can prepare your applications to be able to utilize it. Of course, first, some obligatory notices and disclaimers. Now let's check the agenda. So we'll start with SPDK and its architecture, as well as few examples of the optimizations that we have in place. Then we will cover the performance reports and the test cases that they consist of. And finally, at the end, we'll touch on our continuous performance measurements efforts. Okay, let's start with a quick overview. So SPDK is a set of user space tools, libraries, and applications designed for bleeding-edge storage solutions. It has a rich feature set, is broadly adopted in cloud and enterprise. SPDK is fully open source. It's licensed under BSD license, and we have a great multi-vendor global community. If you'd like to learn more, I invite you to visit our website, spdk.io. As mentioned earlier, SPDK consists of multiple different libraries and drivers that support multiple different protocols. Just to name a few, we have an NVMe driver that supports both PCIe as well as Fabrics, TCP and RDMA. We also have an NVMe over Fabric target that supports RDMA, TCP, and Fiber channel. We have support for virtualized storage protocols such as VirtIO block and VirtIO SCSI. In addition to that, there's a block device layer called BDEV that makes it possible to access various types of devices using block semantics. There are integrations with various existing projects such as OpenStack through its Cinder driver or CSI driver for Kubernetes. We also have integration with RocksDB and various other applications. We have a set of tools that we use for benchmarking, management, and diagnostics. Let's talk about some of the main principles that are used in SPDK design. So since the SPDK is a set of user space drivers and libraries, it's using much fewer system calls than if you'd use a kernel driver. This makes the development process much easier because everything is user space. SPDK relies on polling instead of interrupts. So this means that we have less overhead as there are no context switches to the interrupt service routines, and also gives us better and more stable latency. Finally, SPDK is lockless, so we avoid locks in IO paths, and the threads are kept separate from each other. Whenever they need to communicate, we use message passing that in turn uses lockless queues to communicate. And this all makes it easier to scale. Now I would like to talk a little bit about the threading model. So in SPDK, we have a lightweight thread abstraction library, and it doesn't actually spawn any system level threads. Instead, it relies on a lower level framework to do that. And this lower level framework is responsible for polling and scheduling the threads. These lightweight threads can move across system level threads too, so you need to be aware of that. And this design makes it easy to embed SPDK into existing applications. In order to do that, you need to create SPDK threads on each thread the application is doing the IO from, and then poll it regularly using SPDK thread poll. Of course, the applications that we have in SPDK also need a framework like that. So we've implemented our own called SPDK event framework. And as I've just described, it creates pinned POSIX threads on each CPU core the application is supposed to be running on, and then schedules and polls SPDK threads across them. And this SPDK thread library also provides several very useful abstractions. So one of them is the IO channel and IO device mechanism, which allows the users to store pred thread data called IO channel that is also tied to some object called IO device. We also have interfaces for executing a task on a given thread. So you can use SPDK thread send message to execute a function on a given thread, while for periodic tasks such as polling and NVMe completion queue, you can use SPDK poller to register a function to be repeatedly called on a given thread. I would also like to say a few words about the SPDK NVMe driver. So first of all, it's passive. This means that it only performs actions in response to function calls from the application that is using it. As most SPDK, it relies on polling. And it doesn't use the thread library by itself. Instead, it defines a set of rules that the users need to adhere to. And it can be used either standalone or through the block device layer. And it's the NVMe module in the block device layer that creates the associations between the queue pairs, poll groups, and the threads. A queue pair is just a pair of submission and completion queues that has to be accessed from a single thread, while a poll group, on the other hand, is a collection of queue pairs, which can be from multiple controllers from the same thread, and they are polled as a single unit. This allows us to pour multiple queue pairs more efficiently, but I'll talk a little more about that later on. Now let's talk about optimizations. But before diving into that, let's note that SPDK is designed with performance in mind. And it's that design that lays the groundwork for all other optimizations. Of course, due to limited time, I will only cover a small subset of things that we are doing to make SPDK fast. For more information, I invite you to check our documentation. There's also an excellent blog post written by our colleagues, Jim Harris and Ben Walker. And of course, I also invite you to check the source code itself. Let's start with MMIO. So with NVMe, MMIO is used whenever you update durables. Performing an MMIO write puts a request on a hardware queue so that it's later sent over PCIe bus. And this can be costly because the CPU will stall when the queue is full. So in order to avoid that, we need to find a way to reduce the number of durable writes. So how we can do that? So let's check the completion queue first. So to notify a drive that will read a completion queue entry, we need to increment the head durable. We could do that each time we see a new completion queue entry, but we could also just scan the completion queue, find all new completion queue entries, and then write the durable after that. This is very trivial, and probably all NVMe drivers are doing that, but I still think it's something worth mentioning. The diagram on the right is shows a simplified call stack from an SPDK application. I will be using similar diagrams to showcase the optimizations that we are doing throughout this presentation. Now, what about the submission queue? So the submission queue durable needs to be updated whenever a command is submitted to notify a drive that it needs to start processing it. So for example, when a user requests some data to be read, we need to prepare an SQE, ring the doorbell, and then the drive will start processing that request after the durable write. That means that we have as many durable writes as there are commands submitted by the user. But remember, in SPDK, we are polling. So when submitting a command, we can just prepare the submission queue entry, but delay writing the durable to the next poll cycle. So the user is free to submit one request, then submit another one, and then yet another one. Then finally, when the queue pair is polled, we can check if that durable needs to be updated and do it there, but do it only once. This allows us to avoid as many MMIO writes as there are requests submitted during a single poll cycle. So in this example, we've reduced it by a factor of 3. Of course, this is a trade-off, right? We trade latency for avoiding the MMIO. However, we are polling very frequently anyway, so we find that this is definitely worth doing and yields significant performance improvements. So next, syscalls. So I've mentioned earlier that when you use SPDK, you reduce the number of syscalls. And that is true, but we still have to do some syscalls. So for example, we still rely on the kernel for networking. So with NVMe over TCP, we still need to do calls like send message and receive to transfer the data. And of course, each syscall requires a context switch to the kernel, which is pretty costly. So we want to reduce the number of syscalls as much as we can. So let's see what we can do about it. Let's start with send message. So each time a user submits a request, we need to write out a PDU to the socket. So the most straightforward way to do it would be to do it during submission. But that results in a send message call for each request. So what we can do about it? Again, we can delay it until the next poll cycle. So we can gather as many requests as we can, then do a single send message call with an IOVEC array filled with the buffers for all of those requests. As you can see, this is very similar technique as we did with submission QDorbos, right? Because we are polling, we can batch some requests together between the poll cycles, and then during the poll call, process them all together. This is a pretty common pattern in SPDK, and we use it throughout many different libraries. Now let's take a look at the optimizations around receive. But before we begin, a short notice. So since we are relying so much on the polling, we don't want our threads to ever block. We want them. We want the thread polls to be as fast as possible. So they should check if there's some data to be processed, and if not, return immediately. This is why we are marking all of our sockets as non-blocking in SPDK. To check whether there's data to be read on the socket, we could call receive on each file descriptor tied to a socket, but that would cause a lot of receives. That would usually just return that there's no data to be read. This is where the poll group concept comes into play. So we are grouping multiple queuers and their file descriptors together, and that allows us to poll them all at once using a single epoll wait call. After that, we discover which queuers, which file descriptors has some data ready, and call receive on those only. Next, message zero copy. So message zero copy is a flag introduced in Linux 4.14 that can be passed to the send message call to instruct the kernel not to copy user buffers, but instead pin the pages that contain the buffers to avoid copying the data. After that, the user is notified of the completion by reading the error queue. Of course, this mechanism has trade-offs. So pinning pages has a cost, and we also need an extra receive call to read the error queue. But from our benchmark, it seems that for our storage workloads, this delivers significant performance improvements. So we are enabling it by default in the NVMe over Fabric target. And Karol will show you the impact that using this optimization has in our benchmarks. Another thing that's important to keep in mind is when talking about optimization is, of course, the CPU cache. So this is a pretty complex topic, probably could be a separate presentation. But nevertheless, I think it's worth to mention some of the things that we can do. So whenever a data is accessed by the CPU will pull the entire cache line from memory to the cache. And of course, the cache is very limited. So pulling one cache line will evict another one. So we want to be extra efficient with the structures that are used often, usually, for example, in the IO path. So the first thing that we can do is to fit as much data as possible. And we can do that by rearranging the fields in a structure to get rid of any holes that were inserted by the compiler due to padding. And this can be done. This can be also done by instructing the compiler not to insert the padding for example, using directives like packing. However, it's better to do that by hand because it maintains data alignment in all fields in the structure. Another thing that is worth doing is separating the data based on whether it's hot, meaning it's accessed very often, or cold. So for instance, we can group data that is accessed during each I/O while moving to one cache line, while moving stuff that is only accessed in case of errors to another cache line that is separate from the first one. We can also group things, but whether they are accessed during submission or completion. So, for example, the things that are accessed during both submission and completion paths can be in a common set of cache lines, while those that are only accessed either in submission or completion can be moved to a separate cache line to avoid thrashing. Finally, some compiler options. So for optimization level, we are using O2. We've tried using O3, but we didn't see any significant improvements, so we are sticking with O2. One interesting compiler optimization is LTO. It allows the compiler to treat all translation units that make up a program as a single unit and then optimize it as such. This means that, for example, it can inline a function from one C file in another one. This results in a more efficient code, and we haven't observed any drawbacks to using that, so we are enabling it in all our benchmarks. And Karol will actually show you the impact this option has on our benchmarks. Profile-guided optimization is another very interesting technique. So it's a mechanism that compiles the code in a way that it outputs profiling data. So you run your benchmark, gather the profiling data, and then recompile the code with that profiling data in hopes to achieve better optimization. However, this method might skew the optimization based on the benchmark suit, so the resulting machine code might not be optimal for every use case. And this is why we don't feel like it's fair to report numbers using that option. So we are not using it in our performance reports. However, we still have this option in our build scripts, so you can build your application with PGO enabled. Before I give control over to Karol to talk about the benchmarks and performance reports, let's mention the tools that we are using for benchmarking. So first, FIO. This is an industry standard tool. It's very flexible, has tons of options and different metrics. And to use it with SPDK, we have developed two plugins, one that is using the NVMe Driver directly, and the other one that is using the BDEV layer. But we also have a set of our own SPDK performance tools. They are less flexible. They don't offer as many features as FIO and maybe some other tools. However, they are better optimized for the SPDK model of submitting IOs. And because of that and the reduced feature set, they have much less overhead. And similarly to the FIO plugins, we have two tools, NVMe-perf and BDEV-perf, that either use the NVMe driver directly or use the BDEV layer. Okay, that will be all from me. Karol, the stage is yours.
Thank you, Konrad. Hello, everyone. My name is Karol Latecki, and I work together with Konrad on SPDK project. I will continue with next part of the presentation where I will talk about how SPDK's design, architecture, and software features perform when they are put to test during performance benchmarking. So first, let's talk about what do we at SPDK mean when we are talking about I/O performance. The first metric is IOPS per core. SPDK pulls hardware from user space, and with this metric, we can measure how efficient is SPDK in doing that. The second metric that we mentioned is the I/O core scalability. We measure how the I/O results change as we use more core to perform I/Os. As for the latency, polling has the effect of reducing latency and its variability. We measure the average latency and tail latencies up to 4 nines. For testing performance, we use 3 storage usage models, which are local block storage, networking storage, and virtualized block storage. We use 2 block sizes in our tests. Small workloads with 4 kilobyte block sizes using 100% random read workloads, 100% random write workloads, and 70-30 mixed random read-write workloads. For large block sizes, we use 128 kilobyte block size with sequential 100% read workloads, 100% write, and 70-30 mixed read-write workloads. For each of tested storage types, we apply settings for optimal performance. Typically, for each tested storage, we have a common set of configurations that apply either to hardware setup, for example, considering hardware NUMA alignment, BIOS configuration like power performance settings or maximum power draw. And for some of the workloads, we use additional specific set of settings. On example of NVMe over Fabric tests, we disable default system interrupt balancer and configure the interrupts ourselves so that it matches the NUMA alignment on the system. And also make some system level tuning, for example, in regards to TCP buffer sizes using sysctl settings. Our benchmarking is a time and resource consuming process. So there's a question, do we need to benchmark every release? The answer is pretty obvious in case of any hardware changes that were done to the test systems used for benchmarking process. We try to update our hardware configuration so that the hardware doesn't become a bottleneck over time for the software that we're testing. And the answer is also pretty obvious after making optimizations for any critical paths in the code. But what about software changes which, for example, introduce new features that seemingly should not have any impact on the performance? And in SPDK, we have a rule to benchmark after every release, so we can check SPDK's performance change. Has it improved or degraded? It also gives us an opportunity to highlight the benefits of any software optimizations or new features that have been added during current release development. We publish the reports on our website, SPDK.io. The link is included in the presentation, and if you follow the URL, you will find detailed reports about our benchmarking effort. In the upcoming slides, we will give you an overview of what's included in those report documents. Let's start with local block storage. For the local block storage, we have 4 test cases focused on measuring efficiency, scalability, and latency of SPDK NVMe block layer. We configured the benchmark tool to use SPDK NVMe block devices. In the first test case, we run a small block workload with high QDEP and measure the maximum number of IOPS that we can get on a single CPU core. We do the same also with just using NVMe Driver so that we can show the overhead of using the block layer instead of using NVMe Driver directly. For the second test case, we increased the number of used CPU cores and measured the performance scalability with addition of those new CPU cores. In the first test case, we run workloads with QDEP set to 1 in order to measure latency. We do this for both SPDK block layer and kernel block layer using FIO, libIO, and IO Uring engines to be able to compare them. In the last fourth test case, we limit the number of I/O cores and test the performance scalability as we increase the queue depth. Okay, let's take a look at some example efficiency results. Those results come from a system with 22 NVMe SSDs and Ice Lake CPUs installed. You can find detailed hardware specifications of our platform at the end of this presentation. The workload we're using is 4K random read at QDEF 192. Those results are from running the tests on just one CPU core. We were able to add up to 5 NVMe SSDs until reaching peak performance of 6.4 million IOPS. Next, let's take a look how the I/O path in SPDK and NVMe BDEV scales as we increase the number of I/O cores used by the benchmark. For 4 kilobyte random read workload, the IOPS scale linearly to almost 30 million IOPS with 5 CPU cores, which saturates the NVMe SSDs disks installed in the platform completely. We can also observe linear scaling for random write and random read-write workloads, not reaching as high IOPS as random read because of the SSD's hardware specification. We can also see similar results coming from test case 4, where we limit the number of available I/O cores and scale the workload queue depth instead of CPUs to test both SPDK and kernel block layers. For the block layers, for SPDK and NVMe BDEV and kernel block layer tested with FIO, libIO, and IO viewing engines, you can see that the performance is similar up to about QDEV 16. Beyond that number, we can see polling implementation of SPDK showing benefits as the performance difference between SPDK and kernel becomes clearly visible. Okay, next, networking storage. The test objectives here are to primarily measure the performance of SPDK and NVMe over Fabric's target and initiator components. We also compare the performance between SPDK and its kernel NVMe over Fabric counterparts. And we perform those tests using TCP and RDMA transport layers. The test cases are as follows. For test case 1, we test SPDK NVMe over Fabric's target core scalability. We are using various read-write mode and QDEV combinations with increasing number of cores to reach network link saturation. In test case 2, it's pretty much the same as test case 1, but this time we focus on core scaling test for the initiator side of the connection. For test case 3, we measure latency of SPDK and kernel NVMe over Fabric components. We use random type workloads here with QDEV 1, and using various combinations of SPDK and kernel components used on both sides of the connection allow us to test SPDK and kernel interoperability and its impact on latency performance. And finally, in test case 4, we measure how performance changes with increasing number of connections to NVMe over Fabric's subsystems. Our test setup consists of 3 server systems. The target is the storage node installed with 16 NVMe drives. The other 2 systems are initiator connecting to the target. And all systems are equipped with high bandwidth network interfaces so that the network link does not become a bottleneck for performance testing. Our tool of choice for this benchmark is FIO. With plugins, it can be used for both SPDK and kernel initiators and allow easy comparison between them. All right, let's take a look at some example performance data for storage over fabrics. We've picked TCP for this presentation, but if you're interested in RDMA, then please check out our performance reports at SPDK website. As you can see in the chart for 4K random read workload, the I/O performance scales linearly up to 8 CPU cores, and SPDK target is then able to process well over 100 gigabits per second of traffic. Further adding additional CPU core results in less linear performance improvements and peaks when 24 CPUs are used at about 200 gigabits, which saturates the network link between target and initiators. For the workloads using large block size, like 128 kilobytes, just a few cores are enough to saturate 200 gigabit network link. And in most cases we have tested, just a single core is more than enough to serve 100 gigabits of network traffic. Earlier, Konrad mentioned introducing new software features and optimization as a way to improve I/O performance. And the results in this chart can serve as a good example of showing how important those software improvements are. The dark blue bars are the results of 20.01 SPDK release, and the bright bars are from 20.04 release. In 20.04, we introduced message zero copy into our TCP target. And as you can see, this resulted in over 100 performance improvement for target when running with a single CPU core. Okay, time for the third storage type that we test, which is virtualized storage. Here we utilize SPDK Vhost to provide local storage as a process to expose block devices to other processes like virtual machines. The benchmarking process and the test cases here are similar to what has been already told in the previous sections. And the test cases focus on measuring the I/O when using a single thread SPDK Vhost target, testing SPDK Vhost scalability with addition of CPU cores, checking its performance when serving I/Os for a large number of VMs in the system, and finally testing latency and IOPS with increasing queue depth. Let's see some numbers now. When running core scaling tests, we check vhost, SPDK vhost, with various combination of vhost stacks and SPDK block device types. And in this chart, we can see results for both SCSI and block vhost stacks using NVMe and logical volume block devices with up to 36 virtual machines attached to vhost controllers. And with our current hardware setup, we were able to get a peak result of about 7 million IOPS. Here we can see results which show IOPS when SPDK is constrained to use just 4 SPDK cores. We expect that each VM to be able to process 10,000 IOs per second, and SPDK vhost target is able to meet those expectations and serve 72 virtual machines. As another example of importance of optimizations, I would like to mention and show the benefits of previously mentioned LTO, link time optimization, which is one of SPDK build options. Using LTO for the build process allowed us to increase the performance results up to 7.6% compared to non-LTO builds. Currently, we're doing all of our benchmark tests with LTO enabled by default. Few words about our continuous performance effort. So in the previous part of the presentation, we mentioned that SPDK benchmarks are done on per release basis. And to be honest, that's not 100% true. The full benchmarking process concluded with a performance report document is indeed performed per release, but we also have a quick version of those benchmarks running as part of our continuous integration systems. These are not the equivalent of our per release reports, but serve us primarily as a tool to early detect and report any introduced regressions. Just as you can see in the screenshot in the slide on the right-hand side with a bug report. Thanks to this earlier regression, nothing can stop us in our way to achieve even more IOPS. You can find the live version of the dashboards along with the results at performance.spdk.io. And just one more slide to show how the performance dashboard looks like. The trend is easily visible in the charts, and the tables on the right provide information with raw numbers, along with commit hashes, dates, and any information that can be used to identify a faulty change that introduced the regression in the code. And now, finally, what about those 80 million IOPS mentioned in the presentation topic? Well, all of the topics we've covered so far, SPDK architecture, code design, features, along with benchmarking process and continuous testing process, this all contributes to overall performance levels achievable by SPDK today. Besides regular per release benchmarks, our colleagues, Ben Walker and John Kariuki from our team did some additional tests and experiments and were able to squeeze out a bit over 80 million IOPS on a typical 2-unit Xeon-powered server system with a great average latency of just around 15 microseconds. Okay, thank you all for attention, and we hope you enjoyed our presentation.